What's going on, everybody? Welcome back. Today we are going to create a neural network to classify whether or not someone is likely to get a diabetes diagnosis within the next 5 years based on their current health data. So let's take a look at this. This is the script that we're going to end up with when we're finished here. This creates our neural network and trains it. But before we go ahead and do that, I'm going to talk briefly about what this data set is. So we have 8 different measures. So the number of times pregnant, plasma glucose concentration, diastolic blood pressure, triceps, skin fold thickness. So a lot of various data that could correspond to the possibility of someone getting a diabetes diagnosis within the next 5 years. So anyways, let's run our script here so you guys can watch this model as it's trained and you guys can see how this process works. All right, so here it goes. We're initializing our script now. This is going to begin training the model. And so here it goes. Now our model is training. You can see it started off with an accuracy up here around 64%, and you can see our accuracy is rapidly increasing as the model adjusts based on the input and the output data that you're training it on. Okay. So for those who aren't familiar, a neural network essentially is a function approximator. So you give it an input and its corresponding output, and then it's going to try to map that input value to that output value. Okay, so it's going to do that a bunch of times, and then you can give it new input values, and it will give you a predicted output value based on the previous input and output values that you trained it on. Okay, so that's what's going on here. We have the input values, which are these attribute informations. These are the variables that correspond to certain predictive indicators for diabetes, and then you have the output value, which is whether or not that person received a diagnosis for diabetes within the next 5 years. Okay, so once it trains on that data set, and I'll put the link in the description for the data set, and we'll walk through how you use that as we create the script and as we create this neural network. But this is the data set here, so you can see we have this is CSV file, so comma separated values, which are essentially just each value separated by a comma, so it makes it easy to process it, or makes it easy for us to process the data set. And then we have our first 8 values are the corresponding values that correspond with the data that makes up the possible predictive indicators, and then we have the 1 or the 0 in the final as the final value as to whether or not that person was diagnosed with diabetes. Okay, so we'll leave this here training so you guys can watch that as it goes, and now we'll pull up the script and we'll talk about that. Okay, so our script here is essentially, so what this is doing is we're creating this model, and this is awesome. We're using Keras for this, which is a Python library for creating neural networks. A very, very simple way to do it. It allows us, we use TensorFlow and possibly Theano as 2 backends. So those are other 2 Python libraries for creating neural networks, but they're more ground level. They get more into the nitty gritty details of this. With Keras, we are able to do this very, very easily. Okay, so what we're doing here is we are importing Keras, and we're importing sequential indents from the Keras library, and then we're importing NumPy as well in order to analyze our data set. Okay, so just quick stop on the right here, you guys see our accuracy is getting up now to 83%, and we just finished. So we've got 83.2% accuracy. So now our model, based on those input variables, can predict with 83% accuracy whether or not a person is likely to receive a diagnosis for diabetes in the next coming years, which is pretty good. That's pretty insane, and I know you guys can think about what is possible with that. It's incredible. There's so much. So, I mean, just to go off on a short tangent here, based on the amount of health data that we currently have, we have just mountains and mountains and mountains of health data, and we can use these models to train on that health data for you and I and for everyone in order to better predict and better classify and better understand ourselves and what we're at risk for moving forward in the coming years. You think of when your doctor is making classifications or making decisions, diagnosing you with things, they're using comparatively very small amounts of data in order to make their decisions. Whereas with these models, we can take into account for lots and lots and lots of variables that your doctors might not even be able to account for. So that's the power of these networks in this circumstance. But anyways, here, so we're going ahead and we're importing these modules, and then we're going ahead and we're loading the Prima Indians data set, which is the data set that contains all of these values. Okay. So I'm going to put the link in the description for that. You guys can go and copy and paste that link in there as you guys are creating it. This is what it looks like here. This will be the link. Again, it'll be in the description. But we have, again, the first 8 values, which are the values for the corresponding physical inputs or physical predictive inputs more based on our health data. And then we have the final value, which is the classification as to whether or not a diabetes diagnosis was made. Okay, so next up here, we are loading our data set. So we're using the NumPy library in order to do this, which is a very efficient library for processing data. And so we're loading that data set in here. So we go ahead and we create a data set variable, and we assign that to numpy.loadtxt, which is the function that will load that text data set for us. And we are passing the name here, so Prima Indians Diabetes.csv. And as far as downloading that data set goes, guys, I will show you guys briefly the command as to how we're going to do that. So what you guys are going to want to do is you take that link and you type in wget or wget, and then you're going to put the folder that you want to save your data set in after that, and then you go ahead and you put the name that you want to save the data set as. So in this case, we're going to save it as prima-indians-diabetes.csv. Okay, so you go ahead and we'll say, you go ahead and put wget, and then we go ahead and we'll do user, and then you put the name of your user. So in this case, it would just be, for me, it's owner, and then you put user owner, and then if you say you had your folder on the desktop, you go ahead and you put desktop there, and then you're going to put, say, you've got your project folder for this. Okay, so we're just going to say name the folder diabetes, and then you can go ahead and put diabetes as the folder name, and then you can go ahead and that will save it directly into that for you after you put the URL there. You can also specify the name. So in this case, we're just going to say Keras diabetes or Prima Indians diabetes.csv. Okay. All right. So once you have that, and then you put quotes and then the link that I have in the description, end quotes, and enter, and it will download that data file for you into that folder, which is where we need it. Okay. So once we've got that, we're going to load up this data set, and we have the delimiter, which is a comma. So that just basically means that in between each data value that we have in our file, it is a comma. So next up here, we're going to go ahead and split the input and the output variables. So when we are training our neural networks, you have your input variable, which is going to be, or variables in this case, which are more or less your features, or in this case, our body data or our health data, right? So that's going to be our input. So you can imagine, I want to pull up quickly what a neural network structure looks like. Okay, so just to briefly talk about this here. So here's the diagram. It looks like a pretty fancy diagram, but don't be intimidated by this. So essentially, these features here that you see, x1, x2, x3, x4, those are the input features. Those are the input values. So each value in our data set as we move across here, so 6, 148, 72, 35, etc., are going to be input values. As we move down, those would be assigned to x1, x2, x3, etc., right? And then it feeds forward into the network, but we're going to talk about that in just a minute. So that's how you can visualize the data coming into the neural network, okay? So that's what we're doing here. We're creating the X variable, which represents what is going to be our input layer. So this layer right here, and then we are slicing the first 8 values of each row in our data set in order to create that, okay? And then we have our Y variable, which is going to be the final value in our data set, so classifying whether or not diabetes is true or false based coming in the next 5 years based on the data. So this is data that was collected previously in order to determine this. Okay, so next up here, we are creating our actual model. And this is where Keras is freaking awesome, okay? Because Keras makes this so simple. So we go ahead here and we declare a variable called model, and we say equals sequential, and then you're opening and you're closing parentheses. So what this is doing is saying that we are creating a model that we are going to construct sequentially. So we are going to define each layer as we move across. So again, you have your input layer, you have what are known as hidden layers, you can have multiple hidden layers. In this case, this network only has one hidden layer, but you have your input layer, your hidden layers, and then your output layer, okay? So yeah, we're creating our model. We're saying it's sequential, and then we are adding the number of layers. So we have model.add, and we're adding a dense layer. So this is what dense means, is that densely connected. Okay. So you guys see how each of these nodes here have these lines connecting them to every other node in the following layer, and then every single input node is connected to every single, or neuron is connected to every single neuron in the next layer. That means dense. That is densely connected. Okay. That means densely connected. So we're defining a layer. We're saying it's a dense layer. It has, in this case, it has 12 neurons, and we're saying the input dimension. So this is for the input values. Okay, so this is going to be these are the 8 values that are coming into our network. Those are the input dimensions, okay? So you only need to define that when you are creating your initial layer, which is taking in that data, okay? Next up here, we have our activation, which is using the ReLU activation function. So what does that mean? Okay, so essentially when this data comes into our network, we are multiplying it by a matrix of weights. I'm gonna put up another video that goes into gives an intuitive explanation of this, because I don't want to go into too much of the detail here in this video. But essentially, we're taking in some data, we're performing a bunch of different operations on it, and then we're taking that big huge number and we're squishing it down. Okay, so in the case of ReLU, we're basically taking that big huge number and we are either assigning a 0 or a 1 to it. Okay, there are other activation functions that you can use, such as Sigmoid and tanh, but in this case we're using ReLU because, generally speaking, ReLU is the most effective for training your models in an efficient way. Okay, so just to show you guys what ReLU is, this is ReLU. Oh, this is perfect. Okay, so we've got Sigmoid here. So your Sigmoid activation function maps it as a value between 0 and 1. So it takes that big huge value that we got from our input layer after performing all those complex operations on it, and it squishes it down into a value. In the case of Sigmoid, is between 0 and 1. Any value between 0 and 1. In the case of ReLU, it is 0 or 1. Okay, so again, we'll talk way more about what activation you might want to use when you're creating these networks, and why the ReLU activation function tends to be the most commonly chosen one. But in this case, these are the activation functions, and what you need to know is each layer takes in the data, complex operation, squishes the data, passes it forward into the next layer. Okay, so next up here, we add another layer. And again, it's going to be a densely connected layer. This one has 15 neurons, and again, we are using the ReLU activation function. So this layer is receiving the input from that. Other than that, this layer that we just created here, the first one, it is then passing its output value after squishing it with the activation function into our next layer, which has 15 neurons. So every neuron in that first layer is then connected to every neuron in that second layer. It's passing the values forward. It's performing more complex operations, and then it is then squishing the value again with the ReLU activation function. Okay, so next up here, we have another, we're adding more layers. We're adding more layers in order to represent more abstract features. We'll talk about what that means and why the neural network does that in a video I'm going to put out soon called like an intuitive explanation of neural networks. Okay, definitely good to watch if you guys are new to this. It'll really kind of make things very simple, use very simple concepts. Okay, so again, we're adding another layer here, and this is again another densely connected layer. It has 8 neurons. The number of neurons you can specify somewhat arbitrarily. Again, it's a lot of experimentation when you're creating these models in order to decide whether, or in order to establish the best model for your specific problem. Some of them will use a lot of different layers with few neurons. Some of them use a lot of neurons with a few layers. Some of them will use a lot of layers and a lot of neurons. So it all is going to depend. It's a lot of just experimentation. You can't really know ahead of time. I mean, you can have a general idea, but you can't really know ahead of time what the best way to do it is. There's a lot of time spent optimizing and tweaking your models. Okay, so next up here, we have a densely connected layer with 8 neurons and another ReLU activation function. So again, you can just imagine these layers lined up here, right? Each layer is receiving input, is performing the complex operations, it's squishing the value down using the activation function, and then it's passing that value into the next layer. Okay, and then again the same exact thing. Takes the value that is received, performs the complex operations, squishes it down, passes it on. Okay, so again, that's what we're doing with this layer, and then we have another layer, 10 neurons, densely connected, ReLU activation function, passing it on to our final layer, which is the layer which is going to map the value between 0 and 1. So in this case, this is our output layer, or what you might hear called Y hat. Well, again, we'll talk about that in the next video. Don't worry about Y hat for now. But in this case, this is our output. This is the value that is going to determine, or is going to is our model's answer for how likely, based on those that health data, how likely that person is to be diagnosed with diabetes in the next 5 years. Okay, so we go ahead and we have a sigmoid activation function for this, and the reason we're using sigmoid is because, again, when we take a look at this here, right, we have our sigmoid function. It is mapping it between 0 and 1. So that is some value that is like 0.1, 0.01, 0.01, 0.001, etc., right? Anything between, or 0.71, 0.51, okay? Anything between 0 and 1, it is mapping that value for us. Okay, so that is our output. That is going to be the likelihood, okay? So after it performs all those complex operations, each layer kind of represents more abstract features that are, we don't really know what those features are. Those are what the neural network, that's how it's learning. It's learning to represent those features that it determines based on the data input that we give it, okay? And then it has that output. All right, so now we go ahead and we are compiling the model. So, okay, on each forward and backward pass, which is known as an epoch. So a little bit of terminology here. Do learn this terminology, okay? So as we move forward in our network, I'm going to pull up that diagram of the network again here so we can see this easily. Okay, so as we move forward and backward through our network, so each pass, right, so we get our initial data and we're passing through the network. So coming through a layer, boom, doing all those operations we talked about, squish it, pass it to the next layer, etc., until we perform a complex operation, squish it, and then that is the output layer. Okay, that is our final layer. So after we get our output, what we want to do is figure out how close was our output value to what the actual value was, right? Because when we're training our network, at first it has no idea. It's just like a young child. It has no idea what the correct answer is. But we are training it, so we are saying that once it gets its output, so we give it the input data, it's like, okay, I think this is the output, but then we're like, okay, this is the real output, and then based on the real output, I want you to take the real output versus what your output was and figure out how much you messed up, adjust accordingly, and then try again, okay? So that is something that is known as gradient descent, and that is, okay, so two more terms, okay? The cost function. So the cost function is how much the network's answer missed compared to the actual answer, and then the gradient descent is how we adjust the complex operations that we perform in each layer in order to more accurately reflect the actual answer that we should have gotten, okay? So essentially, that's what we're doing here. So that's what we're saying when we say compile the loss with this loss equals binary cross entropy. What that is just that's the cost function, okay? That is how basically, based on the network's output, how much did you miss by, how much did the network miss by, we'll figure it out, we'll represent that as a value, and then we will adjust the complex operations that we perform in each layer of the network accordingly based on that value. And so when we are training our network, we're doing that lots and lots and lots of times, okay? So in the case of the network training that we saw over here, we did this 1,000 times. So that's what epoch is. So essentially that forward pass where we come up with our prediction, and then the backward pass where we adjust how we come up with our prediction based on how accurate we were. That is what's known as an epoch. That is a forward and backward pass. That backward pass is known as gradient descent, okay? These are important terms to know, but if you guys don't get it right now, that's okay. Repeated exposure is good, and I'm going to be coming up with a video on just a very intuitive explanation so you guys can understand the overarching concepts that make this up, okay? And then we have this optimizer, which is Atom, okay? So Atom is basically just an efficient way to apply gradient descent to our models. I'll link to a paper actually that discusses that if you guys want to learn a little bit more about that. But essentially, Atom is just an efficient way to apply gradient descent to our model. So essentially, you're basically, again, that is based on how much we messed up. Let's adjust the complex operations that we compute at each layer, and that is gradient descent. And we want to do that as efficiently as possible. So we're using the predefined Atom parameter, which is again part of Keras, in order to do this. Okay. Then we go ahead and we want our metrics. So how we're measuring the accuracy of the model, or how we're going to measure the model, and those are our metrics, and we want the accuracy. Okay. So now we go ahead. So now we have our layers constructed. We have we'll start from the beginning. We have our data set that we added in. We have our layers constructed. So we have our neural network constructed. We are compiling our neural network, specifying that we want to find how much we messed up by, optimize our complex operations, or weights as they are known, with the Atom with the atom gradient descent optimizer, and then we are going to go ahead and we are putting out our accuracy. Okay, so we're going to go into more specifics about these things later in our next video, but again, this is just giving you guys exposure. This is a cool model to create, definitely, so you can see this and then you can get a feel for what's going on. Okay, so next up here we are calling the function to fit the data. So this is essentially initializing our network, and we're saying we given our data, so x and y, given x inputs and y outputs, go ahead and do 1,000 backward epochs, so forwards and backwards passes, in order to update yourself, so the model can most accurately predict the output based on our input data. Okay, and then we have a batch size, so we'll talk about that more in the next video again, guys. But batch size is essentially just an efficient way of training the model. Okay, so next up here, we are evaluating the model, so we are creating the scores variable, and we are saying model.evaluate xy, which is again a function from the Keras module, and then we are going ahead and we are printing out the module or the model metrics and the scores, so we can watch as it trains, and then we can see our final accuracy value. Okay, so again, let's go ahead and we're going to run this one more time here so you guys can watch this train. All right, so and any questions you guys got, I know this might have been a little bit more complicated, so any questions you guys have, go ahead and leave them below, and keep your eyes open for the video where we discuss a more intuitive explanation of this, so you guys can again get repeated exposure to what's going on here and learn in the best way possible. Okay, that's what I'm here to help you guys do. I'm here to help you guys learn this in the best way possible, because this is a more complex topic, but it can be made intuitive. It can be made easy to understand, and that's what I'm trying to do here for you guys. So anyways, here's our model training. You see we're going through our epochs. So remember, our epoch is our forward pass, getting our output value, and then our backward pass. I just realized I'm doing that backwards on the camera, but our forward pass to get our output, our backward pass to adjust our weights to using gradient descent after we get our cost function right, in order to make the complex operations more accurately reflect the predicted value. And so that's what we're doing. We're doing that a bunch of times. Those are our epochs. Those are what's training. And at each point here, we are seeing our loss function reduce. So that's good. We want our loss function to reduce because that means our predictions are more accurate. And then we are seeing the accuracy of the overall model increase. So that is the accuracy of the model based on our training data set. All right, so that's what's going on here. Yeah, any questions you guys got, definitely leave them below. I really hope you enjoyed this video. We got a lot more in machine learning on the way here. So thank you guys very much for watching. If you enjoyed this video and thought it was informative and helped you guys, a thumbs up would be great, and be sure to subscribe. Thank you guys for watching. Have a fantastic day. Keep learning machine learning. All right.